Assalamu alaikum warahmatullahi wabarakatuh and a very good morning. So today we're going to cover another topics under the quality management system course. And the topic is called SPC, which stands for Statistical Process Control. So what is SPC? So SPC is an analytical decision-making tools which allows you to see when the process is working correctly and when it is not. So SPC is actually a tool, analytical tool. So you can use these particular techniques to ascertain whether a process is working correctly or not. If the process is not working correctly, then basically you can take action to ensure that the product coming out from that particular process is good. The quality of the product that's coming out from the particular process is per the specifications. Okay? And the concept of SPC is basically based on the detections of variability in the process. So variations is present in any process. So whatever process that you're having, there'll be a variability, there'll be variations. For example, if your process is measuring the length of a pencil using, let's say, for example, vernier, so as the pencil came up from the production line, and as you measure them, there'll be variability. You won't be able to have exactly the same length of the pencils all the time. So there is some variability, there's some variations, right? So what SPC does is basically it identifies when the variations is natural or unnatural. So the variation that's happening in any production line can be natural or can be unnatural. So natural variation is caused by uncontrollable factor. For example, the variability of the temperature inside the room, so on and so forth. So if those are considered as the natural variations and is acceptable in your process, then basically the SPC will be able to detect it. But let's say, for example, if something unnatural happened, some external forces occurs that actually affect the process, then the SPC will identify the variability or the variations as the unnatural variations. And based on that, if unnatural variation present, identifications of the root cause and corrective action are needed to control the quality. So basically, SPC is a tool that you can use in any process, in any either manufacturing process, service in service sectors, so on and so forth. And what it does is actually you can use it to detect if there is any unnatural variations that's happening in that particular process. If there is unnatural variations that's happening in that particular process, then you have to identify the root cause and take a corrective actions to fix it. This will ensure the quality of the product coming out from that particular process. So before we go any further with regards to SPC, let's understand the history of SPC a bit. So SPC was actually developed by Dr. Schwartz, who's working in Bell Telephone Lab in 1920s. This is in the United States of America. So he was conducting a research, and the objective of the research is to find a method on how to improve manufacturing quality and also to lower the cost of manufacturing. So those are basically his aim. And based on that particular research, he developed a concept of control with regards to variations. So the research is basically the outcome of the research is a concept on how to control variations. And basically, he came up with a statistical process control charts. And this statistical process control chart is the heart of SPC. And these charts provide a simple way to determine if the process is in control or not. So using this particular chart, you can actually you can assess the process, whether the process is in control or not. If the process is in control, then the variability that happening in that particular process is natural variability. If the process is not in control, then basically it indicates that there is unnatural variations happening in that particular process. So after that, Dr. Deming uh, built upon Schwartz's work and took the concept to Japan following World War II. There, the Japanese industry adopted the concepts, resulting high quality of Japanese product. So when Dr. Schwartz developed the concept of SPC, he actually developed it for the purpose of usage among the manufacturing companies in the United States. But at that particular time, most of the company in the United States, they did not uh, adopt this particular concept. So it's not that popular in the United States back then. So then World War II happened, and at the end of the World War II, before the surrender of Japan, so when General MacArthur signed the declarations of surrender with the Japanese counterpart, one of the items that's being agreed upon in that declarations is United States going to help Japan to actually rebuild its industry. And one of the help that United States offering Japan is to send statisticians to Japan and teach them on how to implement statistical concept to rebuild the industry. So they sent Dr. Deming to Japan. And Dr. Deming brought with him the concept of SPC. And when he introduced this particular concept to the industry in Japan, uh, the Japanese industry adopted the concept. And based on that particular concept, then basically they improved the quality of Japanese product to a point that they actually beat the quality of the product manufactured in the United States. One very famous example is Toyota quality system. So Toyota quality system is actually the foundations of that particular Toyota quality system is the concept of SPC. So Dr. Deming is very famous from Japan and considered as the god of quality in Japan. So if among the industry in Japan, whenever you talk about SPC, when you talk about the quality concept, then Deming is very famous. Not right now, he's very famous not only in Japan but throughout the world. He's one of the one of the quality guru in the world. So today, SPC is used in manufacturing facilities around the world. So that's basically the history behind the SPC. Okay, going back to the SPC. So SPC is one of the most widely accepted and adopted analytical tools to improve product and service quality. So if you want to improve quality and reduce cost, and you can use these particular techniques. It doesn't matter whether your particular end in mind is a product or service. So if you are in manufacturing industry that produce product, or you are in service industry that offers services, then basically you can still use SPC techniques for this. And SPC is one of the 7 QC tools techniques. So if you talk to any quality improvement experts, one of the tools that being widely used to improve quality is called 7 QC tools. And one of the important tools of these seven QC tools is SPC. Okay, since we mentioned about 7QC tool just now, I just want to introduce 7QC tools in brief to all of you. So 7QC tools basically consist of seven tools, seven quality control tools that you can use to improve quality of a product or a service. And it consists of Pareto charts, process flow diagram, cause and effect diagram, check sheet, histogram, scattergram, and lastly is control chart, which is SPC. So we're going to concentrate on SPC in this particular lecture. Just a bit more on 7QC tools. So 7QC tools was developed by Dr. Ishikawa. So after Deming came to Japan after World War II and start to disseminate the knowledge on SPC that was developed by Schwartz, Dr. Schwartz. So there are many other statisticians and researchers on quality control in Japan. So one of them is Dr. Ishikawa, and if you ever heard about the fishbone diagram, so the fishbone diagram was developed by Dr. Ishikawa. So Dr. Ishikawa developed these seven QC tools, and the seven QC tool is known as also as the democratizing statistics. And the reason why it's being known as democratizing a statistic, um, because the concept of 7QC tools is developed is so that the statistics being used to improve the quality become very easy to be understand by everybody. So basically, that's the whole idea behind 7QC tools. So the basic seven tools make statistical analysis less complicated for average person. So that's the whole idea behind 7QC tool. You want to make sure that the statistical analysis that's being used to improve the quality is not complicated and can be accepted, can be understood by the average person, because even productions workers online should understand 7QC tools in executing their work. A good visual aids makes statistical and quality control more comprehensible. So basically, 7QC tools has a lot of statistical analysis and quality control, which was transformed into visual aids. So it's graphical representations of statistics. So that actually is the understanding and also the implementations and also the acceptance of 7QC tools among all levels of people that's involved in manufacturing activities, from the manager to the engineers to even to the operators. So let's focus on the SPC now, statistical process control. If you remember just now when we defined what SPC is all about, so SPC is an analytical tool for us to make a decisions whether the process is in control or not. So what does it mean? It means that using SPC, you can do two things. One is to make a decisions whether the process is stable or not. That's the first part of it. And secondly is to make a decisions whether the process is capable or not. So these two components of SPC is very important and come hand in hand. So we're going to look into both components of SPC in detail. So the first component of SPC is process stability. So what does process stability means? So process stability refers only to the voice of the process. So what it meant is basically the decisions that you're going to make with regards to process stability will comes from the data and the analysis of data of the process itself, not comparing the process data with other things, but the decisions will be based on the data from the process itself. Okay. So, looking at the process using an agreed performance measure to see whether the process forms a stable distributions over time. So there are a few keywords in here. So when you refer to voice of the process, meaning that you're going to look at the process using the agreed upon performance measure. So this is the first keyword, performance measure. So what does performance measure means? So performance measure means that whatever characteristics of the product or the service that you use to measure the quality of a particular product or services. For example, so if I'm in the business of industry of making, let's say, pencils, right? So maybe one of the performance measure that I measure that I collect from that particular process to reflect the quality of the product coming out from that line is maybe the length of the pencil. So I want to make sure that the length of the pencils is within certain specifications. So the length of the pencil is the examples of performance measure that we are referring here. Okay. So, uh, so, uh, so looking at the process using an agreed performance measure, for example, in the examples that I mentioned just now, is the length of the pencil, to see whether the process forms a stable distributions over time. So what it says is this. So if I measure the length of the pencils over time, let's say, for example, I take the length of the pencils that's that's produced by a particular process. Let's say, for example, for a period of 1 hour, and within that 1 hour, maybe I collected 100 data of the length of the pencils. So, so process stability is looking whether the process form a stable distribution over time. So meaning that we want to see whether the data I collected, what data, the length of the pencil, forms a stable distributions over time. Stable distributions means that whether it form normal distributions or not over time. So if this is for example, if this is let's say, for example, if I collect a data, let me see, if I collect a data and I plot it in this curve, uh, okay, let me try to explain these using illustrations. um, so we are talking about the concept about process stability. So again, looking at the process using an agreed performance measure to see whether the process form a stable distributions of the time. So what this means is basically we want to look at collect data on the performance measure. For our examples, the performance measure that we use just now is the length of the pencil. So we can have x and y axis here, and the y axis would be the length. So this will be length. Let me change this to pen. So this will be length. Maybe the unit would be in centimeter, and the x-axis will be a unit of time. So this will be time. Maybe this is in minutes. So I'm going to put a number of the scale. So maybe the length of pencils in the range of 10 centimeter. So this will be 10 centimeter. Maybe it's 9.9 over here. 9.8 centimeter. This is 9.7 centimeter. This is a random number that supposedly the length of the pencil will be. Right? So this will be 10.1. This is 10.2. This is 10.3. Right? And this is maybe we take a sample of a pencil coming out from the production line, maybe every 5 minutes. So every 5 minutes we take one sample. So this will be 10, this will be 15, this will be 20, this will be 25, this will be 30, this is 35. So what I do is basically, as the productions of the pencils running, then every 5 minutes I'll take one pencils and measure the length, and I jot down what's the length would be. So I'll do this for 5 minutes, 10, 15 minutes, 20, so on and so forth, right? So this is an example. So to actually to come up with the distribution curve, you have to take more samples compared to this. But this is an example. So let's say, for example, the first reading at 5 minutes, the first sample at 5 minutes, when I measure the pencils, maybe the length is at 9.5, 9.9, right? So at 10 minutes, maybe it goes up to 10. At 15 minutes, maybe it's also at 10. Maybe at 20 minutes, then maybe I have a pencil. The pencil length is at 10.2. Maybe at 25 minutes, the 25th minutes, the length of the pencils at 9.9. At the 30th minute, at 10.1. So I'm just putting this at random arbitrary number just to give you an examples of how to do this. At 30 minutes, we go back to a 10, and maybe at the 40th minutes, it will go somewhere, not sure, maybe somewhere here. Here, right? So basically, you keep on collecting this data, and based on this variability of this data, then you need to analyze the data and to see whether this data forms a stable distributions over time or not, right? So the stable distribution definition is basically whether this particular data conform to the normal distribution curve, right? With some requirements. So what I can do now, I can transform this time curve into distribution curve. So I can make a histogram out of this. So in order for me to make a histogram, then the y-axis will be the same units, will be length. This will be in cm, right? And the y-axis now become frequency. So basically, for this, I can count how many frequency of pencils that has the 10 cm length or 10.1 cm length, and so on and so forth, and I transfer those data in this histogram chart. So let me do that. So let me just change the pencil into line, right? So for the length of 10, I have 1, 2, 3. I have three frequency of 3. So this will be 1, 2, 3. So I have that, right? For 10.1, I have 1. 10.2, I also have 1. For 9.9, I have 2. And 9.8, I have 1. So if I collect this data, for let's say, for example, 30 data points, then I can plot more data here in terms of distribution curve. And what I need to do now is basically uh, to look at this histogram and see whether it confirms to the normal distribution curve or not, right? So if it's confirmed to the normal distribution curve, then basically we are saying that the process is stable. So I need to compare this to normal distribution curve, right? So if it confirms the normal distribution curve, then basically we're saying that the process is stable. If not, then the process is not stable. We're going to go into detail on how to do some analysis and what should be additional thing on this graph to see whether this process is stable or not in a bit more detail later on. Okay, so there are two components of SPC. One is process stability and the other one is process capability. So we have covered the process stability portion of it just now. So let's focus on the process capability. So process capability is measures of the goodness of the process. So how do you measure the goodness of the process? It's by comparing the voice of the process with the voice of the customer. And the voice of the customer here is the specification range, which is tolerance, and or the nearest customer specification limit. So in order to ascertain whether the process is capable or not, then you have to compare the voice of the process with the voice of the customer. So we have talked about the voice of the process just now, and this is basically looking at the process cap stability itself. So when we look at the process stability just now, basically use data from the process itself, and that's called voice of the process. So you want to compare the voice of the process with the voice of the customer, and the voice of customer is basically based on the specification limits or specification range specified by the customer. For example, on the length of the pencil just now, so the customer might have a specifications that the length of the pencil must be 10 centimeter plus minus 0.1 centimeter. So that would be the voice of the customer. So to ascertain the capability of the process, you have to compare the voice of the process, which is the data that we collected on the length of the pencil just now, to the specification range that's dictated and specified by the customer. And you should not do the process capability analysis until your process is stable. Means that the data collected over time must be stable, and stable means that it should conform to the normal distributions curve. um, so let me try to illustrate the concept of process capability, the goodness of the process, by using similar examples that we did for the process stability definition just now. So I'm going to draw a histogram curve. Basically, the y-axis would be again length. So would be, sorry. So this would be length in cm, right? And in the x-axis, this is a frequency. So at this point we have collected the data with a function of time, of the length of the pencils, right? And then you transform it into a histogram. So again, I'm going to put some value here in terms of length. So this is 10, 9.9, 9.8. This should be 9.7. This is 10.1, 10.2, 10.3. So I'm going to plug in the number, the frequency for the data that I might got, and this number is basically a random number that I just plucked from the air, just to explain the meaning of process capability. So maybe at 10, the length of 10, you have maybe 4 or 5 units, right? Length of 10.1 centimeter, you have like 3. 10.2, maybe you have 2, right? And then at 9.9, you have maybe 2. 9.8, you have 1, right? And basically what you do is you compare the data that you have with regards to the normal distribution curve. So if it's confirmed to the normal distribution curve requirement plus some other requirements, then process is stable. Once process is stable, then you can conduct a capability study. So let me just draw a normal distribution curve on top of that histogram. So the normal distribution curve might look something like so, right? So again, so we want to compare this voice of the process to the voice of the customer. Let's say for this particular pen, the customer says that the length must be 10 centimeter plus or minus 0.1 centimeter, right? So basically I can draw a specification, upper and lower specification limit for this particular process. So if I do that, basically let me change to line. So the lower specification limit will be 10 minus 0.1, which is 9.9. So the lower specification limit is this, right? The upper specification limit is 10 plus 0.1, so it will be this particular line. So now I have this is upper spec limit, this is lower spec limit. So if you look at this, then basically you can say that since this is a specification limit, even though your process is stable, but you are making quite a bit of bad units that you have to reject. Because you have these units in this particular area, these units beyond the upper spec limits, which does not conform to customer requirement. So if this is the case, then you are saying that the process is not capable because you're producing too many bad units when you compare to voice of the process, what your process is capable, and to the customer requirement. Right? So this is the case where you're saying that the process is not capable because when you compare the voice of the process to the voice of customer, you're making so many rejects. Right? Okay, so what does the good process capability looks like? So again, so this is the length in cm. Again, this is the frequency, and then this is basically the 10. This is 9.9, 9.8, 9.7. This is again 10.1, 10.2, 10, 10.3. Sorry about this writing, it's a bit hard to write using this pad. Okay, so I'm going to make this curve over here. So let me just change it to line and F16. So again, 10 is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And at 10.1, I have 3. 10.2, I have 2. So 9.9 I have 2 and 8 I have 1. So again, I'm going to draw a normal distribution curve roughly. Sorry, right? And let's say, for example, for this particular product, the customer said, okay, my specification limit is 10 plus minus 0.3. Then basically I can draw the upper and lower specification limit, right? So if I draw my upper and lower specification limit, well, what I will have is this. For the lower specification limit is 10 plus minus 0.3 become 9.7 somewhere here. And the upper specification limit is basically 10 plus 0.3 is 10.3. So this is my upper spec limit. This is my lower spec limit. So if you look at this visually, then you're saying that most of the product that you're going to make is basically within the specification limit of your customer. So you're making good product. So your process can make a good product. Not 100%, but most of it a good product. So this is the indications that this process is capable process, and this process is not capable process. So when you look for process capability, basically this is what you are measuring. You are measuring the voice of the process, what your process can do, to the voice of the customer with regards to specification limit. We are going to go in detail on how to do this analysis with proper number equations and assumptions. Okay, so far we have looked at the general the definitions of SPC, which has two components. One is the process control, and then the other one is the process capability. So let's focus on detailed methods on how to come up with process control analysis. So for that, then we have to develop control charts. And the basis of control charts is basically run charts. Okay, and run charts are used to plot data based on time. So this is talking about a chart where you're going to collect data with respect to time. What it does is it examines the behavior of variables over time. So it looks at the variables over time, whether it fluctuates or not, whether it's stable or not, so on and so forth. And it's very useful to identify trends and cycles. So another usage of this run chart is to identify trends and cycle. Is it trending up? Is it trending down? Is there a cycle where every, let's say, for example, 10 hours, then the variables that you collect and you want to monitor actually goes up or goes down, right? So, and the x-axis is usually the time element, and the y-axis is the process to be tracked. So the x-axis is usually the time element. So the x-axis will be time. Maybe it's in day, in hours, in minutes, and so forth. And the y-axis is the process to be tracked. So this is what you measure, the variable that you measure. And run charts is the basis for control charts. And what you want to do for this run charts, for the purpose of control charts, you're looking for pattern. You want to look for pattern. So do not indicate how much variation is acceptable or normal. So, but patterns do not indicate how much variation is acceptable or normal. So on top of the run charts, we have to do other analysis to turn the run charts into control charts. This is examples of run charts. So if you look at this particular run charts, so this is the title here is surgical prep on time as a run chart. So this data is basically surgical prep time. So before surgery, so how long does it take for the prep time, for the preparation time taken by the surgical team? So and they're tracking this as a function of time, and the time is in month. So what they do, maybe they average out the surgical preparation time taken for that 1 month and get 1 point, one data point, so on and so forth. Right? So if you look at this is, again, this is examples of rank chart. And if you look at the rank chart, on the x-axis would be time. So this is time, this is time. So in this particular case, it's in month. And on the y-axis is the variables that they want to measure. And for this particular time, particular examples, is the surgical prep time. Right? So they can see the fluctuations of the surgical prep time as a function of time. Right? So you can see some fluctuation up and down, and also maybe if you can see some trend of the fluctuation, where the time of preparation time seems to peak in January, right? In January timeframe. So there are some interpretations that you can do with regards to the run chart. But this is not a control chart. This is not a control chart. There are other things that you have to do in order to turn this run chart into control chart. So looking at the trend of the run chart, the pattern, so on, so forth, does not indicate whether this particular process is in control or not. Yeah? So there's not sufficient information here. So what we need to do is basically we need to develop a control chart. So in order to develop a control chart, we need to establish a control line, upper control limit and lower control limit, which we'll discuss in the next slide. Okay, so before we go in detail in terms of how to do some calculations, some analysis with respect to the control charts, I just want to show to you the difference between run charts and control charts. So this is run charts on the left, and on the right is control charts. So what's the difference? Difference is these two lines. These two lines. This is called upper control limit. Usually is designated by that writing is too small. Basically, that's designated by UCL, upper control limit. And there is another limit, another line at the bottom of the graph is called lower control limit. So mostly to convert control charts, run charts into control charts, you need to do some calculations, some analysis to develop these two lines. One is the upper control limit, the lower one is lower control limit. And the line in the center is a mean, is the average of all data points. So with this, then basically you have complete control charts. So these are the comparison between run charts and control charts. Let's look into a bit more detail on the control charts. So what's control charts for? So control charts indicates if the process in a control stable state or not. So basically, using the control chart, we can tell whether the process is in control or stable state or not. If it's not, means that there's something wrong with the process and we have to take action on how to correct the situation. So visualizations of the variation in the process can be used to regulate the process. It tracks the output of the process and its conformance to the company's standard. So this is what the control charts can do. So by looking at the control chart itself, it gives the visualizations of the variations in the process. So variations again is not good, but you can escape from it. In any process, there'll be variability, but how much variability can be accepted. So control chart will tell you that, and it can be used to regulate the process. So if the control chart can tells you whether the process is stable or not, then basically you can use it to regulate your process. If it's not stable, then you can stop the process and take an actions on how to make sure that the process is back within its usual range. Okay? It tracks the output of the process, and it conforms to the company's standard. So it can track the output of the process, and you can see whether it's beyond the control limit that's specified by the company. So you can use that for to check whether the process yeah, is confirming to the company standard or not. As long as the process stays within the upper and lower control limit of the process, then the process is said to be safe and normal. So this is the generic guideline, but there are other conditions that need to be fulfilled by the charts in order for it to be said to be called safe and normal. So again, mentioned earlier, there are two lines here on the top and at the bottom, and this is called upper control limit. The bottom one is called lower control limit. So as long as the data stays within the upper and lower control limit, then you can say in general that the process is safe and normal. Again, we're going to go into a bit more detail on how to identify some trends that cause the chart to be called abnormal. Okay, and observations made outside the limit are irregular and problematic. So if they say, for example, you're tracking this data, and all of a sudden the next few lines is actually falls outside or either upper or lower control limit. So if it's outside the control limit, then you can say that the process now become irregular or problematic. So if you see that, then basically you need to do immediate action, to take immediate action to identify what's wrong with it, and you need to take a corrective actions to make sure that the process falls within the upper lower control limit again. Yeah. So if you see that the data is moving outside from the control limit, then you need to be researched to improve the quality. So you have to find out what's the root cause, fix it to make sure that it falls within that move back to within the control charts. The process that consistently stays safe is a good quality process. So you want your process to be within the upper lower control limit. And this control chart consists of what? Consists of mean line, the black one, and you have two additional line. The top and bottom is called upper control limit and lower control limit. Okay, let's take a look at how to establish the lines in the control chart. There are three lines as mentioned just now. One is the mean line at the center, and you have two additional line. One is upper control limit, the other one is lower control limit. So let's focus on the mean line. So the black line at the center is called a mean line. Basically, this is how you calculate it. If individual measurements are subgroup, mean equals to subgroup average. So if let's say, for example, if every single measurement here, see, so let's say every single measurement here, this is one data point, one data point. If this data point consists of a subgroup, yeah, consists of subgroup means that this data point may be the average, the mean of let's say three points. So this is called a subgroup. This is called a subgroup. So you can have either subgroup or you can have individual data point. So if the individual measurements shown here are subgroup, then the mean is equals to subgroup average. So how you calculate this mean is equals to the subgroup average. Okay. If individual measurements is individual data point, then the means is equals to average of individual point. So you can also collect this data this data, and every single point representing one individual measurement. So if this is one individual measurements, then basically the mean is equals to the average of individual points. Right? So let's say, for example, if you have all these data point, right, and this is data point can be either a subgroup or it can be individual data point. So to get this line is basically you add them up. So this is basically summations of all the x from I equals to 0 to I equals to n, right, divided by n. So that's the average, right? So summation of all these data point, this plus this plus this plus this plus this, divided by number of data point. So if you do that, then basically you get this particular line, which is called mean line. Okay. The control limits, the upper and lower control limits is established at the plus or minus 3 sigma. Sigma is standard deviations from the center line, right? So this is sigma. So this is the capital of sigma. So this can be represented by small sigma. Right? So this is so the establishment of this control limit is basically at the plus or minus uh, 3 sigma, 3 standard deviation. Right? So this upper control limit is equals to what? Is equals to mean plus 3 sigma. And the lower control limit down here is equals to mean minus 3 sigma. And sigma here is standard deviation. Standard deviation. So control limit established at plus or minus 3 sigma. So the upper control limit is mean plus 3 sigma, 3 standard deviations, and the lower control limit can be calculated based on mean minus 3 standard deviation. Right? So just some explanation about this. For normal curve distribution. So if you have normal curve distributions, looks like this, right? Within the range of plus minus. So if you have this and you have a range from here to here, so this is a mean center line, this is the mean, and this is 3 sigma. Over here this is 3 sigma. So this line is mean minus 3 sigma, this line is mean plus 3 sigma, right? So the data, the populations within this plus or minus 3 sigma, if you have a normal curve, it accounted for 99.73% of the population. Right? So if this is a normal curve, right, again, then if you take mean plus minus 3 sigma, that particularly, from mean minus 3 sigma to mean plus 3 sigma should accounted for 99.73 of the populations, right? So what it says is this. It says that expected more than 9,973 out of 1,000, the data should fall within this range, if it's normal, right? When this happens, then you are saying that the process is in control. So if you have this limit and all your data falls within this point, within this limit, you are expecting that to happen. Yeah? 99.73% of the time. So the probability, if it's a normal curve, for data to fall within this particular limit is 99.73%. Meaning that if the data falls outside from this particular limit, then something might be wrong with that process. Sometimes something might be wrong with that process, telling you that something abnormal, something beyond the normal, because this is normal curve. So from plus minus 3 sigma, it should consist of 99.73 of the populations of that particular samples. If you have a data outside from that plus minus 3 sigma, it indicates there might be something wrong with that particular data. Right? That's what it tells you. So that's how you construct the three lines: the mean line at the center, the upper control limit on the top, and the lower control limit. The mean line, the average line, is basically just the average of the summation of the data point, and the data point can be individual point or can be a subgroup average. Right? And the upper control limit and lower control limit is based on the calculation. The calculation is based on the average plus or minus 3 standard deviation. We're going to look at how to calculate standard deviation next. Okay, let's look into the equations to be used to calculate the means and also the control charts, control lines. So as mentioned just now, the mean line, the average line, the black line, can be calculated by the summation of all x, summation of all data. So you add all these data points, divided number of data points. So summations of I from 1 to n divided by n. So basically you're going to get the number, the average value, where x bar is the average, and its number of observed values, xi is observed value, and this is a symbol of summations. So that's quite straightforward. Now, to calculate the standard deviations, so this is the equation to calculate the standard deviation. So S or sigma can represent a standard deviation. So either S or sigma, both of them represent standard deviations. The only difference is S is a standard deviation for a sample, and sigma is a standard deviation for the populations. So if you want to know a bit more, a bit deeper about what is sample and what's population, then you can review the statistics book, statistical book. So the calculations for the standard deviation is equal to the square root of the summations of xi minus x bar. So x bar is mean. Xi is the individual data. So basically this is the summation of every individual data minus the mean. This data minus the mean, this data minus the mean, this data minus the mean. Then basically you square them and you sum them up. Divided by n minus 1. So n minus 1 is n is basically similar to this number of observed value minus 1. So square root of the summations of xi minus x bar squared divided by n. So this is the calculation for the standard deviation. And again, this is a standard deviation for sample, not populations. If you want to calculate the standard deviation for the populations, then the only difference is basically there is no minus 1 here. So if you want to calculate standard deviation for the population, this becomes summation of xi minus x bar squared divided by n. Right? So that's the difference between the calculation for standard deviation of a sample and standard deviation of a populations. In our classes, most often than not, we're going to calculate standard deviation of a sample. Okay, let's take a look at how to calculate the means and the standard deviations in order to construct the control charts. So again, the determine the average. The examples determine the average and standard deviation for the height of 7 people, and data are given. Basically, there are 7 data altogether: 1, 2, 3, 4, 5, 6, 7. So first, what you need to do is you need to calculate the mean. So the mean is basically summations of all the data divided by n number of data. So if you do that, basically the summation of all the data, you just add them up. 1.83 plus 1.91 plus, and the last data is 1.87, and then you divide it by 7. What is 7? 7 is number of data points, and you get 1.84. Right? To calculate the standard deviations, again, this is a standard deviation of a sample standard deviation equation. Here you have a square root of the summation of xi, individual data, minus x bar. What is x bar? X bar we just calculated just now is 1.84, right? Square it divided by n minus 1 and square root of that. So if you do that, then basically the summations of the x minus x bar squared is equal to this. So the first data is 1.83 minus x bar mean 1.84 squared plus 1.91 minus 1.84 squared plus, and the final data point is 1.87 minus 1.84 squared. So you sum all those together, right? And you divide that with 7 minus 1, and is 7 minus 1. So if you calculate this, what you get is 0.04. So for this particular examples, then what you get is the mean is 8.84 and the standard deviation is 0.04. So if you basically if you construct a control charts, sorry, the line is not straight. So this will be the height in meter, right? So this will be the mean. So this is the x bar, and this x bar value would be 1.84, and we have upper control limit over here and lower control limit over here. So this is upper control limit, which equals to x bar plus 3 sigma, and this is lower control limit equals to x bar minus 3 sigma, right? So if you calculate that, this will be equals to 1.84 plus 3 sigma is equals to 0.12. So this would be 1.96. So this is 1.96, right? So again, for the lower control limit, x bar is equals to 1.84 minus 3 times sigma. Sigma is equal to 0.04. This is 0.12. So if you minus that, what you'll get is basically 1. So 7.2. So this line would be 1.72 meters. Then what you do is to construct the control chart, you just plot the value in here. So the first one is 1.83. So 1.83 is just below here. Next is 1.91 is somewhere here. And then 1.78 is somewhere here. 1.80, 1.80 is somewhere here, 1.83, even closer here. So I'm not doing it through scale. 0.85, 1.85 is somewhere there, and 1.87, 1.87 would be somewhere or somewhere here. So this would be the control chart for this particular data point. So in general, it's within the upper and lower control limit. So again, in general, we can say that this particular process is in control. However, as mentioned earlier, there are a few other conditions that need to be looked at in terms of trending of the data, which will be covered later on. So let's look into it a bit more detail in terms of what you call a stable and unstable process. So basically, this is the visualizations of a stable process, where the only chance cause of variation present. So basically, the variability for all the process here, there'll be some variability, but the variability is due to chance only. Due to chance only, it's normal variations. So because of that, the process will be in control and easy to predict what's going to happen in the future. This is examples of variability due to assignable cost. So assignable cost means that there's an external factor that you can identify that cause the process to shift. So if you compare these, the individual data distributions here compared to that, so basically the data distribution keep on changing, and sometimes it shifts to the left or right, or sometimes the shape of the curve itself change from normal to abnormal curve. So basically, this is the examples of a process that's not stable and is due to unassignable cost. So how can you tell that this is happening? One is by what we mentioned earlier, by looking at the data. If the data falls outside from the upper and lower control limit, then it's going to be unstable and uncontrolled process. The other criteria that will indicate that the process is unstable as such, shown in this figure B, is this. If you plot the control charts, so this is the mean, upper control limit, lower control limit, and if you have a 7 consecutive data point above or below the average line, then you can say that that particular process is unstable, is uncontrolled. For example, in this case, we have 1, 2, 3, 4, 5, 6, 7 consecutive point below the average line. So this indicates that something wrong, something abnormal happened to the process. So it can be either 7 consecutive point below or above the average line. So this is one of the criteria in terms of the chart trending, in terms of data trending, that actually indicates that the process is not in control. The second criteria is this: if you have a 6 consecutive point increasing or decreasing, then this is also indicating that the process is unstable or out of control. So this is example. You have 1, 2, 3, 4, 5, 6 consecutive data points in increasing trend. So if you saw this, there's something wrong with your data, something wrong with the process. Some external or assignable costs that cause the process to vary as such, right? So you have to stop the process, you have to assess the situations and find the root cause and address it, right? So it can be increasing or decreasing trend, 6 consecutive points increasing or decreasing trend. So this is the second criteria. The third criteria is 2 consecutive points in outer quarter. So basically, you can divide the control chart into 4 quartile here. So this is upper control limit, this is lower control limit. So you can divide into the four quartile in here, shown here. So if you have two consecutive point in outer quartile, then basically this indicates that the process is not in control. For example, on this one, so if these 2 point, two consecutive point here, so if it's normal, then it should shoot back inside the inner quartile in here. So same goes to here, right? So these are basically three additional criteria that indicates whether the process is in control or out of control. So the first one is all data must be within the upper and lower control limit. Second criteria is basically if you have 7 consecutive points above or below the average line, then it indicates the process is not in control. Or if you have 6 consecutive points trending up or trending down, also this indicates that the process is controlled. And if you have 2 consecutive points in the outer quartile of the chart, of the control chart, then this also indications for out of control situations. So whenever you have these out of control situations, you have to find the assignable cost and fix the assignable cost, right? So when you have stable, so these examples of stable and unstable variations. So if you have unstable variations due to assignable cost or causes, it's going to be hard for you to predict the future variations performance. So if you have unassignable costs like this that cause the data to go all over the place, that's very hard for you to predict what's going to happen in the future, and you want to be able to predict what's going to happen in the future. So if this happens, you have to identify the cause and address the issue. So that's basically the explanations and the additional criteria on determining whether that particular process is in control or not, other than using the upper and lower control limit. So we have looked at the how to use the control chart to identify whether the process is in control or not. So again, if it's out of control, then you have to fix it and address the issue. The other thing that you can use the control chart for is to look for continuous improvement, right? So again, this is example of data, a control chart of the depth of a keyway. So you have a product, you have to measure, you have to machine the depth of a certain product, and they call it depth of a keyways. So you measure the depth in millimeters, and basically you plot it on the control chart, right? So again, as mentioned earlier, no matter what process, you have some process variability. So for example, in January, this is the control chart for the depth of the keyway in January, and you can see the spread of the data. Even though if you look at this, even though in general the process is all in control, but it does not mean that you cannot do improvement in it, because variability is bad. You want to reduce variations as much as possible in your process. So basically what you can do is you can work on improvement to reduce the variability of the process, and how you should do that, then basically is depends on the expert in that particular field. They should know what need to be controlled in order to reduce the variations. So control charts can be used to indicate the improvements of reductions in variability as you proceed. So improvement of on the process is reflected by a control chart, recalculate control limit, and means once process is changed. So you can see if you can use a control chart also to reflect the improvement that you have done on the process. So if you look at this, then basically the standard deviations is in February is smaller compared to standard deviation in January, and the standard deviation in July is less than standard deviation in February. So if you look at this, I can say that, so this is a standard deviation, so I just use sigma as a sign for standard deviation. Okay, So sorry, standard deviation for February uh, is 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 greater than the standard deviations of July, and standard deviation of February is smaller than standard deviations of in January. So you can see that the reduction in standard deviations or variability in January, in February compared to January will actually narrow the gap between the upper and lower control limit. So meaning that you control your product tighter. Same with the standard deviation in July is much better compared to standard deviations in February. So this is important because the control charts measures the variability and whether the process is in control or not. If you remember when we discussed about the SPC earlier, there are two portions of it. One is the control charts, whether to determine, to ascertain whether the process is in control or not. And the other one is process capability. So to compare the performance of the process against the customer requirement. So if you can reduce the variability of your process, right, and this will improve the capability of your process when you compare it against customer requirement. So again, you can use control charts to actually reflect the improvement that you make in the reductions of variability. Right? So reductions in variability comes along with the reductions in standard deviations, and you can visually look at it on the control chart by narrowing the gap between the upper control limit and lower control limit, and this improvement will help in terms of the process capability when you compare your process against the customer requirement. Yeah, very cool. As mentioned earlier, the second part of the statistical process control is on the process capability analysis. So, process capability analysis is basically a measurement of how well the process matches the specification. So, if you look at this particular uh, illustrations, so this is the what do you call it? The representations of the process itself, what the process can do. If you remember, this is the mean, okay, and this is the upper control limit, and this is the lower control limit. So this is basically plus minus 3 sigma, right? So this is the process. This is the process. So you want to measure how well the process matches the specification. So what's the specification? This is specification. So this is upper spec limit. This is lower spec limit. So we want to measure whether the process can meet the specification requirement or not, right? For example, so this is basically the example that we used before is the length of the pencil, right? So if the length of the pencil, distribution of the length of the pencil is within this distribution, plus minus 3 sigma, and if the specification is much more bigger compared to what the process can do, then you are saying that the process is capable because you can produce product that actually meet the specification requirement. huh? That's what process capability is all about. And we should only conduct the process capability analysis after we know that the process is stable. How do you know the process is stable? By control charts. By control charts, just now. Okay, so one way to ascertain the capability of process is by calculating capability index. So capability index can be calculated using these particular equations. So capability index equals to upper spec limit minus lower spec limit divided by 6 sigma. And this Six Sigma is basically, if you remember the control charts that we covered prior to this, so the distance between the upper control limit and lower control limit is plus minus 3 sigma. So this is where it comes from. So in these illustrations, okay, let me put here. So this is the representing the lower control limit. This is the upper control limit. This is the lower spec limit. This is upper spec limit. So again, the spec limit is determined by customer usually. And the control limit is basically what your process can do. The what's your process can do, capability of your process. So the distance from upper and lower control limit is basically 6 sigma. Okay, 6 sigma. So what CP does is basically it calculates the relative width between the spec limit and what your process can do, 6 sigma. So if CP is equals to 1 or greater than 1, basically you can say that the process is capable of what? Capable of producing good product per the customer specification, right? So again, if you remember, plus minus 3 sigma for normal distribution covers 99.73% of the populations, meaning that if your CP is equals to 1, then the chances of making a good product would be 99.7%, right? So that's what it meant by CP. CP equals to 1. However, some organization uses CP of 1.33 and 2 as the acceptable number. So again, the bigger the CP, the better it is. The better it is. For example, in this particular case, the upper spec limit minus lower spec limit is this distance from here to here, which is much more larger compared to 6 sigma from here to here. So again, for this particular case, then the CP would be much greater than 1. Okay. So uh, as a reminder, this CP capability index calculations using CP value only valid if the center of the process is at the center of the specification. Again, I repeat, the determinations of capability of a process using CP is only valid if the center of your process is at the center of your specification. However, if the center of the process is skewed to one side, let's say for example the nominal value of your process is somewhere here, which is not at the center of the specification limits, then basically the CP value does not represent the capability of the process itself. For that case, then we need another capability index called CPK. So we're going to cover CPK later on in this lecture.
Flynn had illegal conversations with the Russians, you see, and then lied to the FBI about them. Two wrongs may not make a right, but this president is determined to find out how many do. So the president is certainly acting like a guy whose days are numbered, but he has not conceded. I'll catch you up on the latest details in this never-changing story in tonight's
Gobble, gobble, I suspect foul play. Gobble, gobble, I'm president, and there's stuffing you can do about it. Gobble, 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 gobble.
The road from the White House.
Today, the president was supposed to attend the latest fraud fest starring alleged attorney and pagan priest summoning the Norse god of dentistry, Rudy Giuliani. Giuliani was holding an event with Pennsylvania Republican state senators, but it wasn't an official Senate hearing because they were holding it at a hotel, not at the state capitol. Yeah, it's not an official event. It was more of a fraud fan convention. That's why they called it Election Con. The president expressed strong interest in joining Giuliani for the trip. His first outside of the Washington area since Election Day. His first, but not his last. But this morning, as everyone was getting set to depart for Pennsylvania, the White House announced that the trip had been canceled, possibly because at least 2 people close to Giuliani have contracted COVID-19. Now, no one knows exactly how the staffers got the virus. Possibly they caught it from someone in the president's inner circle, or it is possible they got it because it was the will of the monolith. How long have I been out? Now, despite the positive test, Giuliani went to Pennsylvania anyway, and during the hearing, the president called Jenna Ellis, one of the other lawyers, and she held him up to the mic.
I really appreciate being asked to speak, and I'm in the Oval Office right now, and it's very interesting to see what's going on.
I'm not saying the president has given up on the idea of overturning the election, but I will point out he is literally phoning it in. As I said, this is our country's first COVID Thanksgiving, and the experts are urging us to make it our safest Thanksgiving by not gathering or traveling. Or as one California official put it, just say no to family Thanksgiving. Just say no. I wouldn't use the anti-drug slogan. Now kids are just going to have Thanksgiving in secret under the bleachers. They're going to be huffing stuffing. You can tell from the cranberry ring. One home where they should be really careful this holiday season is the White House. Ever since Election Day, the White House has been circulating 2 things: fake cases of voter fraud and real cases of coronavirus. So far, at least 45 people connected to the White House have contracted the virus. Recent cases include Mark Meadows, Ben Carson, Corey Lewandowski, and Don Jr., all of whom tested positive after attending an election night watch party in the White House. Obviously, they all should have worn masks and kept a 6-foot distance between their lips and the president's butt. Well, the White House has learned their lesson from the election night party: have a different kind of party, because the White House is planning holiday parties indoors despite the pandemic. Well, they have to have the parties. Rudy's already made a batch of delicious holiday head nog. But they're going to take precautions, folks. Food will be individually plated by chefs at plexiglass-protected food stations, and all past beverages will be covered. So the CDC has finally achieved Sizzler salad bar and sippy cup technology. But no matter how many precautions they take, there's always some risk. So the White House warned invitees that attending the parties will be a very personal choice. Yes, it's an important personal choice. It reminds me of that poem by Robert Frost. 2 roads diverged in the yellow wood, and I took the one without COVID because I'm not an idiot. We got a great show for you tonight. Our guest is Rob Corddry, but when we return, I get a visit from the president's personal lawyer. Stick around. Welcome back, everybody. Let's say hello to our friend, Mr. John Baptiste. Hello, John.
Hello. Woo, what's happening with you?
Congratulations. 2 Grammy nominations today.
Yes, indeed. Oh, I'm so grateful and thankful that the music is connecting with people and adding to people's lives.
Well deserved. You and Corey Wong, what's the name of that album?
Yes, Meditations. Meditations with Corey Wong, the incredible guitarist, Wolfpack.
And then your live album from the Village Vanguard.
Yes, Chronology of a Dream. You were there.
I was there. Matter of fact, I was just listening to the very thought of you and Rachel this weekend. Oh. Amazing.
Oh, yes.
You've got my vote.
So much. Hey, now let's get it.
Come on. let's swing this one.
Yeah.
Hey, stick around. I'm about to interview Barack Obama. I think you're going to like it.
I heard. I think I will.
John Baptiste, everybody.
Later on.
Thanks, John. Folks, yesterday I had the honor to sit down with our 44th president, Barack Obama, whose new book, A Promised Land, is out now. Jim?
Well,
President Obama, thank you so much for joining me today.
It is wonderful to be here. Thank you for having me.
Yeah, it's good to see you.
It is good to be seen. I've been seeing you on television, but it's good to see you in person.
That's nice.
And
that's got to help the
Michelle
demo
says-
in some. How old are you? Are you
I am way over your-
between
I'm
18
not-
and 54?
I'm not the demographic you're looking for.
Sorry, it doesn't count.
It's too late.
I apologize. It doesn't count.
Michelle says, "Hey."
Oh, good.
Yeah.
Good.
You know,
Good.
she loves you.
Well, I've really enjoyed spending some time with her over the last 4 years.
I know. And,
Yeah.
And she adores you. She thinks the world of you. I think you're okay.
Can we
Big challenges that Joe Biden's going to have is to figure out how to puncture that, information bubble that not just Republican officials, but a sizable portion of voters are in right now.
That gets you to a question that's buried deep in these pages right here, but it could be the only question I ask you. If I only had one question to ask you right now, it would be, what happens now? What the hell happens now? When you have half or 70% of the Republicans, so maybe about 40% of the public think that Joe Biden won by cheating.
Yeah.
And they believe that all these fantasies being promulgated about Democratic cabals that seem to be pulling the strings in states, Democrat or Republican, all over the United States. How do you then speak to those people, even if you're someone like Joe Biden, who's capable, believes in a government doing the job to serve the people, and is empathetic to the needs and concerns of the people who don't vote for him? Because part of, and we'll get to you eventually, but part of what I think is extraordinary about what we're about to go through is that you know that Joe Biden actually does care about the people who didn't vote for him and why they didn't and what they think. How does he reach those people?
Well, look, I think he's in a good position to make the effort. The fact that he won is indicative of the message he sent of wanting to unify the country. I do think people are exhausted by just this, World Wrestling Federation constant case.
Let's look at the difference between CP and CPK with some examples. So this is looking at the case 1 that we discussed just now, where at this particular for this particular situation, the CP is greater than 1. For this case is 1.2, 1.33. So if you look at this, for this particular example, for this case number 1, the U SL minus LSL is equals to 8 sigma, and the bottom portion of it is equals to 6 sigma. So because of that, then basically when you calculate CP, USL minus LSL divided by 6 sigma is equals to 8 sigma divided by 6 sigma equals 1.33. So if you calculate this, so if the process is center and you calculate CP value, then you get a CP of 1.33. And if you calculate CPK, just to make sure that you remember how to calculate CPK, so CPK is equals to the minimum of either upper spec limit minus x bar or x bar minus lower spec limit divided by 3 sigma. So basically, so if you calculate the CPK using this, then what you have is the USL minus x is equals to here. So this is the x bar. So this is x bar. So the distance from here, if it's center distance from here and distance from here, so this is equals to this is x bar minus lower spec limit, and this is upper spec limit minus x bar. So this value will be the same. This value will be the same. So you just choose either one. You just choose either one. So if you choose either one, then basically what you'll get is I'm sorry. So this is sorry. This is so this from here to here. This from here to here. Yeah. So this is LSL, this is USL's lower spec limit, upper spec limit. So this is X bar, and this is the lower control limit. So this is lower control limit. This is the upper control limit. So this value, where either X bar minus LSL or USL minus X bar, they're the same if the process is centered. So with this calculation, then basically you get to get this will be 4 sigma divided by 3 sigma. Then basically sigma is cancel out. This is you get 1.33, right? So either you calculate CP or CPK, you get the same value because the process is centered. Okay. But if you look at this example on here, so again, this is activate the pen. So this is the LCL, right? And this is lower spec limit. This is upper spec limit. This is X bar. So X bar is here, center, right? So the CPK. So when you calculate the CP, CP is basically 6 sigma, which is the process variability here, control, divided by this value from upper spec limit to lower spec limit, which is 8 sigma. So if you do that, then you get this value 1.33. So that's straightforward. But if you calculate CPK, right? So again, CPK is equals to the minimum of either LCL. So this is X bar minus L SL, or USL minus X bar, right? Divided by 3 sigma. So if you do this, if you calculate this, then what you get is this. So from here to here is the so this is the USL minus X bar, right? And from here to here is X bar minus L SL. So if you calculate from here to here is 3 sigma, right? From here to here is 1, 2, 3, 4, 5. This is 5 sigma, 5 sigma, right? So this is equals to 3 sigma, this is equals to 1. So which one is the minimum? This is the minimum, 3 sigma, right? So because of that, CPK is equals to 3 sigma divided by 3 sigma. So if you cancel sigma, you get 1, right? So in this particular case, then the value for CP and CPK will be different because the center shifted to one side. So what you do is you calculate you choose the minimum between the two, either X bar minus LSL or USL minus X bar, so whichever minimum. And for this particular case, USL minus X bar is minimum, so you get 3 sigma. So 3 sigma divided by 3 sigma, then you get CPK of 1. Right, as shown here. So if it's off center, then basically it tells you CPK and CP will be of different value. For this particular case, the shift is not too extreme, so CPK still equals to 1. So still saying that the process is still capable. But if the process is shifted, let's say for example, if we shifted by this much, right? So you're going to have a rejected part, whichever is produced beyond the upper spec limit. And if you calculate these, then basically the center will be shifted here, and this value, upper spec limit minus X bar, will be lesser than 3 sigma. So when you calculate the CPK, will be less than 1, so it will reflect that the process is not capable. Right? So CP value does not change if the process is off center, but CPK will detect this shift. So that's why CPK is a better measurement of a process capability compared to CP. Okay. Let's take a look at the case number 2. This is again similar to the case that we discussed earlier, where at this particular case number 2, the upper spec limit, the minus spec limit is equal to 6 sigma, and divided by 6 sigma, so you get the CP equals to 1. Right? So for this particular case, then if the process is again center, then the CP value and CPK value will be the same. So if you use CP and CPK value to ascertain whether the process is capable or not, then you will say that the process is capable. However, if the process is off-centered, as shown here, so basically in this particular case, then the upper spec limit is here. So I'm just going to show you this particular line, and lower spec limit is here, and X bar is at here at the center. So it's not really centered here, right? So this is supposed to be a straight line. It's not a bigger line. So the 6 sigma is here. So if these situations, if you calculate CP, you'll get the same value as if it's off center, or at the center or off center. CP will not reflect the off centerness of this particular situation. And if you just use a CP, you're saying that the process is capable because CP is equals to 1. But in fact, whatever produced here at this line beyond the upper spec limit, these are reject material. Right? So actually the process, even though CP is equals to 1, but the process is actually producing a bad material, out of spec material, because it's at this particular area. Some portion of the productions will be producing rejected units because it's beyond the spec limit. So if you use CP to ascertain the capability of the process, then you are making a wrong decision. Right? But if you use CPK, then CPK will reflect the process is not capable of producing good units, and some of the units will be bad. Some of the product produced for this in this particular operation will be bad. Again, CPK is equals to the minimum of either upper spec limit minus X bar, or X bar minus lower spec limit. So this is either this or this. Right? So if you in this situation, then of course you're going to see this is the minimum between the two. So this should be, and this value would be 2 sigma. So if you look at this 1, 2, so this is 2 sigma. So in this case, then when you calculate, this is divided by 3 sigma. So if you calculate a CPK would be 2 sigma divided by 3 sigma. And what you'll get is basically 0.67, similar to that. So the CPK will predict, if you use CPK, if it's off center, then it will predict that, it will tell you that the process is not capable. CPK is less than 1, so it's not capable. And this is the actual situation, because some of the parts will be produced beyond the spec limit. So this illustrates that CP value does not change if the process is off center. So if the process is off center or on center, CP will not be able to detect it. CP shows process is capable even though process is producing out of spec parts. So if you look at the CP value here, CP equals to 1, indicates that the process is capable even though some of the parts will be produced is actually out of spec parts, need to be rejected. So if you use CP, then you will arrive to erroneous conclusions that the process is capable. However, if you CPK able to detect and show that process is not capable. So if you calculate this particular situation using CPK, then the CPK value of 0.67, which is less than 1, indicates that the process is not capable. Okay? So this is a second case to illustrate, the difference between CP and CPK. Okay, let's look at case 3. So in case 3, as explained before, the upper spec limit minus lower spec limit will be smaller compared to 6 sigma. So by default, when you calculate the CP, then CP will be less than 1. So it indicates that the process is not capable. So if the process is centered, then basically both CP and CPK will have the same value. And you can see, so you can see that, okay, you can see that this is the upper spec limit and the line for the upper lower spec limit. This is also the line. So this upper lower spec limit, this is upper spec limit. So whatever that's produced beyond that particular spec limit, which is actually out of spec parts and need to be rejected. So for this particular case, the process is not capable. And if you calculate if the process is off center, again CP value will not change, but CPK value will get worse. So in here, I'm just going to draw a line here. So this is lower spec limit, this is lower spec limit, this is upper spec limit. Then whatever produced in this particular area is reject unit. So in this case, in case number 3, case 3, where the upper spec limit minus lower spec limit is less than 6 sigma, then both CP and CPK are able to detect and show that the process is not capable for this particular scenario. Okay, let's look at these particular examples on the CP and CPK calculations, basically from here you can determine whether this particular process is capable or not. So it's given determine CP and CPK for this process, given that the mean is 6.45, sigma, which is standard deviation 0.03. Upper spec limit is 6.5 and lower spec limit is 6.3. So let's look again at the equations on how to use CP, how to calculate CP. So CP is equals to upper spec limit minus lower spec limit divided by sigma. So upper spec limit here is 6.5, lower spec limit is 6.3 divided by 6 standard deviation, 0.03. So this gives you 0.2 divided by 0.18 and you'll get 1.11. So from this calculation, then you can see that the CP value is 1.11. So this indicates, from the CP value, indicates that the process is capable. The process is capable. Again, this might be erroneous because we don't know whether the process is centered or not to the spec limit. So let's calculate CPK, which will take into account whether the process is centered at the center of the spec limit or not. So again, to calculate a CPK, the equation for CPK is equals to the minimum of either upper spec limit minus x bar or x bar minus lower spec limit, right? So let's calculate the and this is divided by 3 standard deviation 3 sigma. So let's calculate the USL minus x bar. So upper spec limit is equals to 6.5 minus x bar is 6.45, you'll get 0.05, right? And this value x bar minus lower spec limit is equals to, so x bar is 6.45 minus the lower spec limit is 6.3, so you'll get 0.15. So between the two, so which one is minimum? So this is minimum of the two. So we select this value as the value that we put in the denominator in this particular equation. So then we can calculate CP is equals to 0.05, right? Divided by 3 sigma, and 3 sigma is 0.03, right? So what you get is basically 0.05 divided by 0.09. So if you calculate this, what you'll get is 0.56. Okay, so this is CPK, sorry, CPK. This is CPK. So because of that, then basically, if you use CPK as the capability indicators, then basically it tells you that CPK is 0.56. This indicates that the process is not capable. This process is not capable. So with this analysis, then basically you're saying that the process is not capable because of this value. To illustrate what this means in graphical form, let's try to draw this. So we have a line here, and we have the CP value. CP, the upper spec limit and lower spec limit is the lower spec limit is here at 6.3, and upper spec limit is here at 6.5, and the center is 6.45 is skewed to this side somewhere here. So this is x bar equals to 6.452 is skewed to the side. So if you generate the normal distribution, it might look something like this, right? So this is the x bar. So this is upper lower spec limit. This is the upper spec limit. So you can see from this graph that basically the process is going to produce parts over here that's beyond the spec limit and will be rejected. So because of that, then basically the CPK calculation indicates that the capability index is actually less than 1, which is 0.56, right? So the conclusion you can make out of this is basically the process is not capable because the CPK is less than 1, even though the CP is greater than 1. This is because there is the center of the process is not at the center of the spec, as is illustrated by this graph, right? Okay, as a conclusion for this particular chapter, the SPC is an analytical decision-making tool to ascertain if process is working correctly or not. And there are two tools specifically that we have looked at. One is control charts. So we have looked at how to develop a control chart and what it meant and what it's being used for. Basically, it can identify when the variations is natural or unnatural. So if the variations are natural, meaning that there is external factor that's influencing the process, that need to be identified and corrected so that the process will go back to its control situation. The other tools that we look at and look at and also calculate is CP and CPK. Right, CP and CPK is the capability index, where CP is capability index, which cannot detect if the axis at the center of the process is not at the center of the spec. And CPK is a better capability index, which will take into account the shift in the center of the process with respect to the center of the spec. And it determines if the process can make parts within customer specification or not. So control chart is the voice of the process. CP and CPK will check if the process is able to meet the customer specification or not. Okay, so that's the end of this particular chapter on SPC.